are from LBL. So he works in the AMCR division, which I just learned used to be called CRD, within which there is the Quantum Information Science and Technology Group, QIST, and within which we have the AQT, the Advanced Quantum Testbed, which has its own super cool website that you should check out. So Kasra's the head of hardware for the AQT, and he's been in Berkeley for a while, having previously worked at the ALS and done a PhD, in fact, here.
Yes.
Well, welcome. Thank you. I'm looking forward to your talk.
Thanks so much for the invitation. Yes, so I have been at Berkeley for a long time indeed, at UC Berkeley since 2005 and at Berkeley Lab since 2014. Did my undergrad, PhD, everything here. Worked at ALS for 5 years, building a tachographic X-ray microscope there before switching over to quantum in about 6 years ago or so. And I've been following this series, this colloquium for many years. So it's great to finally be on the other side and to give the talk. So I'm going to discuss the full stack, specifically superconducting quantum computer from the instrumentation perspective as a super instrument. And here by a super instrument, what I mean is a collection of instruments that are each individually standalone, could be regarded as instruments, but then they have to work in concert to perform as a unified quantum computer. My own area of research is quantum architecture. So really how you put the pieces together, both in abstraction and in the physical sense. And so I'll try to give a sense of that towards the end. But in the meantime, in the beginning, I'll approach it, instrument by instrument, briefly talking about each instrument. I'll try to have pictures of our team members who are responsible for different parts of the stack up there with their names. And each one of those instruments deserve their own individual talk, but I won't go too much into detail. My aim is to give you an overall sense for the quantum computer. So a little bit of a motivation, the history of, obviously nowadays everyone's talking about quantum computers, but the history of it really goes back to several decades, to the 1980s. Multiple people came up with ideas about building quantum computers. I won't mention every single one. One of my favorite initial formulations of it is by Feynman in an article he wrote titled "Simulating Physics with Computers," in which there's this paragraph that he ends by saying, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." So that was back in 1981. In the years that followed, we had some other formulations as well, but nobody really had a clear idea of what it actually meant to build a quantum computer. How do you even think about the parameters and how you make it operate? And then in the 1990s, some unexpected use cases started to emerge. Probably the most famous one of these is Peter Shor's algorithm for factoring, which are really mathematical. They have nothing to do with simulating nature. And then that started to really pique people's interest. And then the paradigms about complexity classes and what problems are really NP-hard and whether it looks NP-hard in quantum as well and whatnot, all of those started to come out. And that really set everything on fire. And then finally, in 1996, David DiVincenzo, who at the time was at IBM, he wrote a seminal paper. I have the archive screenshot of it here in 1996, and then I have the Wikipedia summary down below, where he stated a number of criteria to try to wrap our heads around what a quantum computer is. So he stipulated 5 criteria for building a quantum computer. Number 1 is a scalable physical system with well-characterized qubits, so quantum bit. Number 2 is the ability to initialize the state of qubits to a simple fiducial state. So basically, initialize everything in 0 so that you know where you're starting from. You have a reference. 3, long relevant quantum coherence times. And coherence times, for those who may not be familiar, this is basically the length of time that the individual qubit can maintain is quantum nature before nature interferes with it. It collapses the state of the wave function, and you no longer have access to computation there. Number 4 is a universal set of quantum gates. Gates are basically operations. Classically, you have AND, NAND, NOR, all these classical gates that you're used to with classical computing. what's important is that in quantum computing, because these gates have to operate on the basis of quantum mechanics, these gates are all unitary, so they have to be reversible. And that's just a completely different way of thinking about gates. An AND gate, classical AND gate, for example, it's not reversible. You can't, knowing the output, you can't tell what the input was. And then lastly, a qubit-specific measurement capability. So once you're done with your computations, a way to read out the state of the qubits at the end. And then he stipulated two additional criteria for quantum communication. One is the ability to interconvert stationary and flying qubits. And two is the ability to faithfully transmit flying qubits between specified locations. So it's basically what we think of today as transduction, to be able to convert the state of a superconducting qubit to a photon, maintaining the quantum information through entanglement and then distributing that entanglement. So this is the first time where we actually had some sort of a definition that could allow us to think about getting our hands on the problem and building a physical system. And then later, a few years later, the very initial examples of qubits were demonstrated, and then by roughly around 2010s is where we had the first examples of what could be called a proof of principle quantum computer. And then the DOE got interested in this by and large, really in the form of large problems that are fit to DOE around mid-2010s. And the first large-scale act was the formation of the Quantum Testbed program, of which there are two. So we have the trapped ion testbed at Sandia called QScout, and the superconducting testbed for the DOE is here at Berkeley Lab called AQT, the Advanced Quantum Testbed. So that's about motivation. Then, so thinking about the full stack quantum computer, there's usually abstraction models that go along. So on the left-hand side here, I have the von Neumann architecture for classical computing that came out of the development of the classical computer. And then in the middle, I have something similar to it for quantum computers that some version of this has been around for the last 10 years. I should have put a reference on this. I apologize. I believe this is from Leon Riesebel's paper. And then on the right-hand side, I've kind of, instead of having all of the little details from quantum algorithm all the way down to the quantum chip, I've summarized it into a few stages that we can think about here. So you have the applications and algorithms at the very top, and then you have the quantum processing units. This is the physical chip that would allow you to do all those operations at the very bottom. And then in between, you have the control system and compilation and QCVB that are related to that. And I'll describe all of these as we go through. And then what is not really noted here is the cryostat. That you absolutely need that, and it's an important instrument, but it's not regarded as like a part of the abstraction model. It's not doing anything computational. But I will dig into that as well, because that's a critical piece of the instrumentation. And then at the very top, you can also add the supercomputer that is becoming more and more a part of the problem. And I'll point to that as well as I go along. And then lastly, I was asked to keep this talk to the undergraduate level because we have folks from all different backgrounds present here from different corners of Berkeley Lab who are not necessarily physicists or computational folks. So those are the parameters. All right, so a little bit an overview of AQT, directed by Professor Irfan Siddiqui. If you go to our website, aqt.lbl.gov, you will be able to find a 3D virtual tour that allows you to navigate virtually through some of our lab spaces, including some of our measurement labs and our fabrication labs. I have some of these components of the full stack that I talked about noted here, the quantum processor, the cryogenic platform, the control system that is FPGA based, and then the software stack. And then the AQT, the aim of it is really to help the community develop quantum computers. And I have some of the principles noted here. Low-level access. So as opposed to, for example, there are quantum computers on the cloud these days by IBM and Rigetti and others, and you can submit your experiments and get your data back. So we don't operate in that way. In fact, if that's all the requirement there is, then we refer folks to those cloud platforms. If the experiments require deep access to get things done, that's why we're there. And we expose with transparency every component of our system. We engage in partnerships and free exchange of information and results to help things grow faster. And in the process, we do a lot of co-design of hardware and algorithms, which is really part of that spirit of the full stack vision. Starting first with that physical layer, the superconducting qubit and the quantum processor. I'm going to just spend a few minutes without going super in depth, but hopefully this will give you an idea of where to start. And then I have Ravi Nayak, Dr. Ravi Nayak, who is our head of measurement at the AQT, who also oversees our device development and quantum processor development efforts. If you have, obviously, folks might have heard of trapped ions and neutral atoms-based quantum computers, and there you get the quantum parameters as nature gives you, right? And then you have the spin, and you have other things that you can manipulate. If you want to build this on chip, then essentially you need to build what is essentially an artificial atom, something that acts like it. It has discrete energy states, like a harmonic oscillator. And if you want to build something like this, obviously the first thing that comes to mind is an LC oscillator that acts like a pendulum, right? The capacitor discharges, creates a potential across the inductor. The inductor throws it back to the capacitor and it just oscillates back and forth. Now the problem is this kind of a system has no anharmonicity. It's completely harmonic, which means there's no addressability. You can't identify and isolate individual energy transitions. So you need a way to know where you start and where you end. You need an anharmonicity, and you can arrive at that if you have a nonlinear element here instead of both of these linear elements. So the Josephson junction is one such element. And because it has nonlinear inductance associated with it, it gives rise to this anharmonic behavior. And what the Josephson junction is 2 layers of superconducting material that are sandwiching an insulating layer, which is usually a native oxide of those superconductors. And then it has parameters associated with it that you can actually engineer instead of being beholden to what nature gives you. And that's partly the appeal of these systems. And this is what it looks like under an electron microscope. And so you can play around with this. You can find different ways of arranging and lumping these superconducting elements next to each other, and that gives you the qubit. And there's a lot of science done here. For example, this is work that we did in collaboration with the Molecular Foundry, where we looked at variations in the fabrication process and how it affects the oxide and the way that might give rise to decoherence mechanisms. So if you improve this, then you can arrive at a qubit that is longer lived, that can maintain that quantum information for longer. So there's a ton of work that being done here. And I'll just flash that just to have that additional piece of complexity there. So this is the transmon, roughly speaking. And then there's other ways of coming up with more complicated topologies to lump these superconducting elements in more fancy ways to provide additional noise resilience properties and other properties. And so our team works on that partly in Professor Siddiqui's academic group at UC Berkeley, but through other fund sources. There's Fluxonium, there's Kirkats, there's other things that we work on. So now, how does this how do you build on top of this to create a quantum processor? So I have here one of the simplest versions of our quantum processors that we started developing actually before the Advanced Quantum Testbed came into existence in 2018. This is called the Trailblazer, and I have the version 6 noted here. So the transmons that I was just showing you, those are color-coded in green here. And then you will see individual drive lines leading up to the transmon that are in kind of bluish color. And those don't really terminate at the transmon, but a little bit away from it. So they act like an antenna. They create an electromagnetic field that interacts with the qubit. And then the qubits are coupled by these resonators in kind of purplish color. So you can basically think of these roughly as like penduli that are mediated, the interactions are mediated by springs, roughly speaking. And this is what allows you to then create entanglement and have the state of one qubit depend on other qubits. So those two elements, the driveline and the couplers, those allow you to run gates and manipulate the state of the qubit. And then to do readout, readout is usually done in multiplex. So here I have the cyan line, that is the common multiplexing bus. And then the red resonators, which are detuned from the frequency of the transmons themselves, those are coupled to the readout bus. And then you can multiplex in frequency the readout tones that resonate with the resonators. And by sensing the phase shift in the resonator, you can infer the state of the transmon. And it is a quantum non-demolition measurement, which means that after you've done your measurement, the state of the qubit is what it is. So hopefully this gives you a little bit of a sense of the problem. Now, this is, as I mentioned, this is the simplest, one of the simplest cases of how you can build a quantum processor. I have some fancier metrics just so that you can see how these systems are characterized. Obviously, you would want to quote coherence times, both for energy decay, which is like 0 and 1, and then dephasing, which is, think about it in terms of the equatorial motion on the Bloch sphere. And both of those coherence times are important. And then I have some fidelity numbers here for the gates. Ideally, you want to have 100% fidelity, right? So if you have 99% fidelity, that means essentially statistically 1 error in 100 operations, which is not good enough to do anything of meaningful value beyond what you can do classically. And then some more advanced metrics noted here. So some version of this chip, we've had this since roughly the mid-2010s at Berkeley. Incidentally, this is the first quantum processor that on which the first demonstrations of simulation of nature was performed. Variational quantum eigensolver here, when Jared McLean was here before moving to Google, developed an algorithm and tested it on this, the earlier versions of this, to show simulations of the molecular spectra of the hydrogen molecule. And then beyond this, you have many different modes of connectivity and coupling that can extend all the way to a 3D flip chip integrated system that allows up to all-to-all entanglement. And then so you gain a lot more modularity and controllability, but at the same time, you lose coherence times, and there's always a trade-off. So our role is basically one of our roles is to explore this design space for quantum processors at lower qubit counts without committing to any single one, and help the community do pathfinding on processor design. So next, I have the cryostat. So these are the shiny pictures that you've seen in the news all the time. So why do we need 10 milli? So these cool down to 10 millikelvin, right? Usually I try to make this interactive, but I'll just say the answers right here. So it's obviously not just to make things superconducting, because you get that at a few Kelvin, depending on your metal. But it's partly also to help thermally isolate the qubit phononically, and also to keep the qubit by default in the ground state so that you don't spontaneously occupy higher states, because information is usually encoded in energy states. Not always, there's other qubits that do other things. But you want to maintain the lowest energy partly for that reason as well. And then, so what is the job of the cryostat? It is to completely isolate the qubits from the environment so that they can maintain the quantum states, but at the same time provide a pathway to control and interact with the qubit. And those two goals are kind of working against each other, right? If you're providing a pathway to manipulate the qubit, that pathway can also serve for noise to get in. And there's a lot of like attenuation and other RF engineering that happens throughout the stack to enable that. As you see, we have these RF lines going from the top, which is around room temperature, and then it cools down in stages to 4 Kelvin, about a Kelvin and 100 millikelvin, down to 10 millikelvin down below here. And there's these RF lines that are going, carrying the RF signals all the way down to the quantum processor. So from an instrumentation standpoint, one of the common questions we get is, how do you cool down to 10 millikelvin? So this is a two-step process. The first step, getting us down from room temperature to 4 Kelvin, that is accomplished using a helium-4 compressor, which you see here on the top right corner. And this is very similar to your household fridge. It's just the gas is helium. And so you compress it in the room and dump the heat into the room environment, send the gas in, it interacts with the fridge, absorbs heat, expands, comes out, and then you repeat that cycle. So that allows us to get down to around 3-4 Kelvin. And then to get from that temperature down to 10 millikelvin, there's a separate process called dilution. And dilution relies on the phase dynamics of helium-3, helium-4 mixture. So this is a separate helium circuit. And if you look at the phase diagram for helium-3, helium-4, you'll see that there's this forbidden region in between. So here on the x-axis, we have helium-3 concentration in the mixture of helium-3, helium-4. And then on the y-axis, we have temperature. So when you get really cold, only extremely low concentrations of helium-3 are allowed in that mixture. And by the way, this is at atmospheric pressure. If you build up pressure to a couple of atmospheres, that has the effect of lifting this phase diagram up a little bit. So then you get to a place where around 2-3 Kelvin, you'll already start disallowing large concentration of helium-3 in the mixture. So then, if you push this mixture through and force it to distill, the liquefied helium drips into this mixing chamber, which I have down at the bottom. And then, as the concentration of helium-3 starts to build up, it is disallowed by this phase diagram quantum mechanically, so it has to evaporate and absorb heat. So it's kind of like a sweating process. It's just the sweating dynamics are dictated by quantum mechanics, roughly speaking. So that's how we get down to 10 millikelvin. And then below the 10 millikelvin plate, we have all this fancy set of stages that allow us to mount the quantum processor, which itself is housed in this cryo packaging under this lid here, wire bonded to PCB and connectorized through these SMA connectors. And this sits at the very bottom of the fridge. And then these RF lines are carrying the signals. And then there's room to thermalize and install a range of RF components to condition the signal. And I won't get into the details of those. So this is the cryostat, and then there's a lot of work that is done to make sure that your box modes, electromagnetic box modes inside the box, don't interfere with the elements on your quantum processor itself. We've had that happen in the past, and then that just results in suboptimal performance. The shielding is important here. So we have the quantum processor here at the bottom. You want to make sure that magnetic noise from the environment, electromagnetic noise from the environment doesn't interfere with the qubits. So there's multiple shielding materials, both superconducting and otherwise, that need to sit around and to isolate the qubit. And so there's a lot of work that is done to make sure that that environment is properly done. So here in simulation, you see about 40 dB attenuation at the bottom of the shielding, so that the qubits don't sense the environment. And then you can actually see the result of that in experiments is when you add all this shielding, the effect is a multifold improvement in coherence times because you're reducing interaction with the environment. Okay, so coming out from the fridge. So we started at the bottom of the fridge with the quantum processor itself, then we had the cryostat, and now inside the room, you have the control system. And so if you think about a quantum experiments are usually represented as these quantum circuits. So each line there on the left-hand side, you see those kets with the state 0 written on them. So you initialize in the state 0, then you run all these fancy gates, whatever they may be. So this denotes your quantum experiment. And then at the end, you do your measurements. So this needs to be compiled into native gates, and then the control system, which is FPGA-based, converts these to pulses, RF pulses, that then are sent down into the fridge to interact with the qubit. So for this is a critical piece of the system. We used to have commercial systems for this. And these are all FPGA-based anyways. We had partnered with, or we have partnered with Zurich Instruments. They are still a partner, and they are still working with us, and we still have a lot of these instruments in-house to help run our experiments. And they are perfectly sufficient for a whole class of experiments. But what we found is that because the state of the field is so nascent, quantum computing is still very much in its infancy. So you really need deep access into the FPGA-based control system to build your own firmware and your own way of doing quantum experiments, because nobody really has it right yet. It's still very much under development. And so we realized that it's actually much better if we have deep access to the whole system. And for that, it's better if we develop it ourselves. So fortunately, we have an FPGA team here in the ATAP division at Berkeley Lab, who've been working with us. And I spent a lot of my time in my first years coding for Zurich Instruments and for these commercial systems to get them to perform. And then I decided to instead invest in the Cubic team here to have them develop the system for us. And while supervising them closely to make sure that the development is rigidly really coupled to the scientific needs of our researchers. So the first version of this was developed in 2018 by Dr. Gang Huang and his team based on the Xilinx VC707 FPGA platform. And then the team developed auxiliary RF components and software and other tools, and these were all open sourced and published openly to help the community grow. Then a bit later, over the last 2-3 years, we've moved over to the recent generation of the third generation Xilinx RF SoCs that have a native sampling rate of 10 gigasamples per second, which allows us to use the second Nyquist zone without a signal up conversion to get out signals in the 5 to 10 gigahertz range if we need to, which is usually what we need. And then the team developed, again, analog front-end components, both RF and DC coupled, for experiments. And then at the core of this is a distributed processor scheme that on FPGA assigns decision-making mechanisms on a per-channel basis to individual qubits. And this partly then enables us to do something called mid-circuit measurement and feed-forward with very low latency. So this is the case where instead of having a static circuit that has all of these gates already programmed in, and then you do your measurement at the very end, instead you can make measurements mid-circuit before the experiment is done. And based on the result of a measurement on a single qubit, decide to modify the rest of that experiment. And this is extremely powerful. You need this for error correction, and you need this for a number of other things. In part, this enabled us to do teleportation-based gates. So I won't get into the details of it, but just very briefly stating, if you remember the first, one of the first slides where I showed you the quantum processor, the physical proximity, the physical layout of these qubits are important, because if you want to entangle 2 qubits at 2 distinct ends of your quantum processor, you need to run swap gates. You need to run some sort of gate to distribute that entanglement one step at a time. So if you have like a 1,000-qubit processor, you need to repeat that process multiple times to get that entanglement to distribute, and that eats into your coherence time. So this is a way, teleportation-based is a simple way to help us get around that and distribute entanglement essentially in a single, what you can think of as a single step. There are reasons why the fidelity is low. Part of it has to do with readout fidelity, and so the overall effective fidelity of the gate doesn't end up being so good. But those are bottlenecks that we know how to address, and we're working on those as well. And then lastly, Gang and his team showed that they can synchronize through a reference clock all of these various platforms, both ZCU216 and VC707, so that the system can be scaled up. And this is the team working on Cubic: Gang Huang, Yilun Shu, Nilay Fruitwala, Abhi Rajagopala, and Neil Vora. And this is a completely open source system. It has been adopted by others as well. Perhaps the best example of this was 2 years ago. I formed a partnership with University of Oxford, and they've integrated Cubic into their system, and they've used it to do some groundbreaking experiments involving machine learning for quantum as well. So the details, I just have a couple of slides that I'll run through quickly, just so that those of us in the audience who are who are FPGA engineers and or RF engineers can have something to look at here in more detail, is so here you have the Xilinx RF SoC, which is a combination of the FPGA fabric, a microprocessor, and some analog components. So Gang and his team developed this analog front end. So this version of it is completely RF, between 10 megahertz to 10 gigahertz, that allows you to take that signal out. And then this other version actually allows you to do DC coupling as well. So this is more modular. There's a differential carrier sitting on the bottom, connected to the RF SoC with individual smaller numbers of channels with different frequencies, handling the needs of more complex experiments. And then there's some amplifiers and other electronics associated with this. And then all of this is sitting in a chassis that was also developed by the Cubic team. And the whole thing has been open sourced and is available to the community. And then here's the data flow. You have the RF SoC on the right-hand side. And then I just have this here to point out the fact that how you represent the quantum experiment and how you compile that into some sort of an intermediate representation and convert that to pulses, that is not really something that the field is unified on. This is still very much an active area of research. And we have been working on this as well, in particular, Dr. Nilay Fruitwala here. And we expose all of these details so that people can modify this as well as we ourselves doing research on it. And then system integration. So from the user perspective, our own internal users, as well as our user community externally, from their perspective, they can sit out and at the top end there and generate their quantum experiments through a number of openly available tools, such as IBM's Qiskit, Google's Cirq, and other tools. And then on the other end, you want these experiments executed on the control system. And then in between, we have this software stack that we've developed called Qtril. It's actually gone beyond just a single software stack at this point, where we have a couple of different flavors of this. And the role of this is to integrate everything seamlessly, so you take care of the compilation and the transpilation, but then also there's optimization tools such as the Berkeley Quantum Synthesis Toolkit integrated into this. And what this does is it takes the effective unitary for a quantum experiment, representing that quantum experiment, and then with a threshold for error. So if you say, for example, that you're willing to take a 1% hit on the overall accuracy of the ideal representation of your experiment, this tool can generate and can synthesize a new circuit that is reduced in number of qubits and in gate depth. And that means then a more complex experiment can be brought within the reach of existing early stage quantum processors. And but that is an NP-hard problem, that kind of synthesis. And so that is done on supercomputers. So in our case, fortunately, we have access to NERSC. So we use NERSC for that level, for some of that kind of work as well. And we've collaborated with NERSC folks. By the way, the future generations of NERSC are supposed to integrate at some point a quantum computer into them. I personally believe right now it's too early to do it, but at some point we'll get there. And so I did help create the NERSC quantum strategy roadmap a year or two ago. So I was involved in a little bit of that, but I won't get into detail about that aspect of it. It is important to point out that at some level, a classical supercomputer can be thought of as as an instrument within a full stack quantum computer. And then once you have that entire set of instruments working together, you can attack the scientific landscape. And so this is a slide I borrowed from Dr. Ravi Nayak. It's not a disjoint partitioning of the scientific landscape, but it's just a way to wrap our head around it. QCVV stands for quantum characterization, verification, and validation. Roughly speaking, you can think of this as ways to characterize and measure different sources of noise and error, and then to develop mitigation protocols to mitigate those sources of noise. This is extremely important, especially in the stage of the development we're in. There's novel quantum control. This is beyond just the control system development, but also multi-qubit gates. Gate development itself is an active area of research. We're not settled yet on a proper set of gates, and these vary by quantum processor itself. Ternary quantum logic. So one thing that you might have noticed that I didn't discuss in detail explicitly is ternary quantum. So we're not necessarily limited to just 0 and 1, right? Because this anharmonic oscillator that I showed in the beginning, it natively has many energy states, and you do have access to that if you properly control it. So you get that essentially for free. This is something that was tried with CMOS-based classical computing as well, but the price you had to pay for it was too high. So we still have binary digits. We just have 0 and 1, classically speaking. But with quantum, it actually becomes easier if you do things right to experiment using Q-trits and Q-quarks and these higher level states. And that means you can arrive at a much more complex Hilbert space using fewer numbers of qubits. And then when you have these two sets of tools, QCVV and novel quantum control, then you can do more meaningful simulations of nature, whether it's quantum chemistry, nuclear spin dynamics and nuclear physics, many-body physics, high-energy physics. You can tackle that. And we've done work at AQT on all of these, and mixing and matching these. So for example, one of the early cases of doing Q-trits, higher level quantum bit systems for simulation of nature, was an experiment we did like 4 or 5 years ago on simulations of information scrambling in black holes using small numbers of Q-trits, just to see, because the dynamics, there are some similarities in the dynamics. So, and I'll leave it at that. You can have multiple lectures on just these scientific applications. Okay, so I think I have something like 10 minutes left, 10, 15 minutes, okay. So that is the end of the instrument by instrument piece of my talk. I'm gonna spend the rest of the time talking about how the pieces fit together and thinking about quantum architecture and giving you some solid, tangible examples of this. And this area is really my own area of research, so this is something that's close to my heart. So architecture, first of all, just to make this salient, you can think of architecture both in terms of classical and quantum, and regardless of how you look at it, you can think of it in abstraction or physical. So here I have layers of the abstraction model. This is an abstract architecture, including von Neumann. The von Neumann architecture really doesn't dictate how you implement each one of these boxes. It just says that this is how you can think of the system. And then you have the hardware-software components of the architecture, and there's architecture in this sense as well. So two distinct senses of architecture, and there's interplay between them. So I should have really put this matrix, the way I think of it is a matrix of classical quantum and abstract and physical. And so what I care personally about is abstract quantum architecture. And so, and the implications of that and the interplay between that and the physical and the classical. And fortunately, we have teams at Berkeley that are working on all these areas, which is what enables me to then be able to do my research on abstract quantum architecture. So another motivating piece before I get into the science, I have this caricature here comparing classical computing and quantum computing. If you study the history of the development of classical computers, and I'm not talking about like 2,000 years ago Antikythera device and things like that, I'm talking about something which you might today recognize as a classical computer. These started developing roughly around 100 years ago. And the optimal system development in the engineering sense, it really happened hand in hand and in parallel with the development of the abstraction model, right? And a lot of it had to do with World War and really locking together a bunch of theorists like John von Neumann together with a bunch of engineers and just telling them, go build something that really works. And they made that happen. And then they stood back and then they inferred the abstraction model for it, which is how we ended up with the von Neumann architecture. In quantum computing, it's actually been upside down. It's been done a little bit upside down, in the sense that the abstraction model, some version of this abstraction model, once we had early proof of principle devices, like 10 years ago or so, 10, 15 years ago, some version of this abstraction model has been imposed top down, and then teams of engineers and scientists have been putting themselves in little boxes, developing systems to fit this abstraction model, which is not optimal, right? Now, there is a reason for this. This has been a necessary evil. I'm not saying that, oh, we've all just been a bunch of idiots and done it for no good reason. There is a good reason for it. And the good reason is because the vast majority of people don't have deep access to a quantum computer. And so this way of dividing up the problem allowed folks from different backgrounds to participate in the problem of quantum computing without having their hands on it, right? Applying the skills that they had to the problem, which is totally valid. But at the same time, this means that if you're beholden too much to this, then you miss out on the opportunities to do proper system engineering and develop proper architecture. And the problem is, because of this mindset, even folks who do have full stack quantum computers, such as many big corporations that I won't name, they've also been falling prey to the same mindset of compartmentalization and black boxing and not doing the proper system development. And I've talked to a lot of their internal scientists and engineers about this, and they're aware of it, but it's just this is the way big corporations are set up organizationally to handle it, right? And this is an area where a national lab like Berkeley Lab has the advantage, because we are all multidisciplinary and we're all working together under one roof. At least in principle, it can really be done that way if you do it right. And so my interest is how to do this architecture the right way, to have a super instrument that works cohesively with proper architecture. And so the rest of this work that I'm going to talk about is centered around the work led by these three teams: the FPGA-based control system team led by Gong Huang, the QCVV and advanced quantum protocols led by Akal Hashim, and microelectronics, room temperature and cryogenic, and classical architecture led by Anastasio Bucco. And I've been trying to basically get the right mode of operation going to bring into convergence the work of these teams. So I'll give you two examples. And the setup for the first example is the types of errors that we have in a quantum computer, in a qubit, let's say, right? So here's the block sphere. Most people are probably somewhat familiar with this. I know that not everyone in the audience is a physicist. This is just a way to visualize the state of a qubit, or the spin of an electron, or something like that, right? So you can think of the block vector pointing anywhere on the sphere, and that denotes the state, the quantum state. And the errors associated with this, you can have an error. So if you run this experiment, now this is obviously statistical, right? This is not deterministic. So if you run an experiment 1,000 times and do a measurement across some measurement basis, you will end up with statistically different results. And an error would be basically an offset in that result, something that is not the correct output, either in the offset or in the statistical behavior. So the two main types of error can be thought of as systematic errors or coherent errors. Systematic is a little bit of a simplification. It's not necessarily systematic. There's a bit more to it. But coherent errors that essentially correspond to an over-rotation, to an offset in the angle of the state you want to be in. And then you can have stochastic noise, which basically means that you're not always a little bit off, but each time you measure, you end up with slightly different end results. And that effectively amounts to a shortening of your block vector. So the block vector will be pointing along the correct direction, is just shortened. And that is essentially a quantum impurity in your measurement. So you have these two types of errors. Now, it turns out, for reasons I won't get into, that stochastic noise is much preferable to coherent errors. You don't want to have any coherent errors. And so how do you mitigate this? So there's this protocol that was first suggested in its current form by Joe Emerson and Joel Wallman out of University of Waterloo, who proposed to us to do this experimentally a few years ago. So if you want to run an experiment denoted here on the left-hand side, this is the Bayer circuit. This is the quantum experiment you want to run. If you do this 1,000 times and keep measuring, you will have some coherent error, some offset in the measurement. So how do you fix that? So what you can do is, around any set of 2-qubit gates in any 2-qubit gate cycle in your experiment, you can insert some Pauli. It doesn't have to be a Pauli, but Paulis are what people do. You can randomly select a Pauli before the cycle, and then look up the undoing Pauli after the cycle. And then when you have this kind of 3 single-qubit gates that are neighboring each other, you can absorb them into each other so that you end up with a different set of gates. And the result of this is you end up with an experiment that looks different, but it is logically equivalent. It ends up at the same endpoint in the Hilbert space. And the good thing is that it's the same gate depth, so it doesn't take you any longer to run this experiment. So your coherence times won't be affected. Like the effective coherence times won't get worse. So now, if you do this, a single randomization won't do anything. But if you do many different randomizations, it's effectively like taking the same, ending up at the same end destination from your initial state, but taking different routes and then averaging them out. And that means that these coherent errors associated with the different routes will be averaged out. So, but the effect of it is that you'll gain more stochastic noise. So you're converting your coherent errors into stochastic noise. And so Akal Hashem from our side led this user experiment with the Waterloo team, which had founded a company called Quantum Benchmark, a startup called Quantum Benchmark, to commercialize this. And so Akal demonstrated here for the first time that this actually works. And these violin plots show that I have the bare circuit in blue and then the randomized compiled version in orange. And the randomized compiled version results in a reduction of the total variational distance to the correct solution. So this actually works. And then later on, Quantum Benchmark was acquired on the basis of a lot of the good work that they did by Keysight Corporation. And this experiment, by the way, this protocol, randomized compiling, it's been adopted by everyone, including IBM and others in the corporate world, and they apply it to their experiments to get better results. Now, the problem here is what I showed you here, all of these randomizations. They take time to compile. The additional randomizations take more, the compiled versions take more time to upload. You need more onboard memory on your FPGA to store and run. And so this takes a lot of time. So this is the problem that I just described. So the question is, can you get the benefits without suffering the downside? Because what people do right now is if they want to do 1,000 shots, they only compile maybe 20 randomizations and run each one of them 50 shots for a total of 1,000. And they get most of the benefit, but not all. But that they make that compromise because they don't want to compile every single one. And so our approach to this was to do this live on FPGA, to store the Pauli set on FPGA, and at runtime per cycle, randomly sample from this Pauli set, store the effective undoing Pauli through a 2-qubit gate, also on FPGA. This is a 4x4 element table, so 16 elements in there, and you can just look this up. And so this part, these first two steps are relatively trivial. The last step is what is not as intuitive, which is that you don't actually need to multiply these 3 Paulis to end up with the result. It turns out that can be parameterized. And it is parameterized by phase. So you can have a 64 element map on FPGA that is phase parameterized, and you can just look it up, insert the phase in there, and you're done. So, and that's the only way you can do it live on FPGA, because otherwise the FPGAs are sequentially slow. So it doesn't make sense to do the multiplication there. So if you do this, then the result is you get randomized compiling completely for free. And here I have some examples with a quantum experiment that has a circuit depth of 100, so 100 gates, circuit width of 8, so 8 qubits. It would take about 12 seconds to run a randomized compiling experiment with 20 randomizations. And if you were to do full randomization per shot, it would take about 500 seconds. And with our scheme here, you can do the full randomization and you do the full experiment in 2 seconds, which is the time it would take to do the bare experiment. So you get this completely for free. So this was led by Nilay Fruitwala and Akal Hashem. We put this on archive last year. We have filed a patent on this, and we've already had folks express interest to license this. And lastly, IBM also cited us and acknowledged that this kind of approach will help them do their experiments in a better way. There's another example. Maybe in the interest of time, I should skip this one. How much time do I have? I'm at the end, huh? 5 minutes? Okay, maybe I'll quickly run through this. So the parameterized circuit execution. So the example I just showed was only applicable to a single protocol, randomized compiling. is there any way you can extend this methodology of co-design to get improvements in other areas? So there's a whole class of experiments in QCVV, cycle benchmarking, randomized benchmarking, gate set tomography. That I won't get into the detail of those. But every time you cool down your quantum processor, you have to recharacterize it before you can run any experiments on it. And these characterization experiments take many hours, sometimes days to complete. So for example, cycle benchmarking, the full experiment has 6,000 circuits in it. Each one of those needs to be run maybe 1,000 shots, maybe 10,000 shots at least. But what we noticed is that only 21 of these 6,000, for example, in this particular case, are structurally unique. The rest of them have the same, they look roughly, when you look at the quantum circuit, it looks roughly the same. It's just that the parameters are a little bit different. And so my postdoc, Abhi Rajagopala, he came up with this methodology called rip and stitch, where you inspect the full set of circuits, the full 6,000, identify the ones that are structurally unique, and compile only those circuits. And then from the rest of the circuits, extract the gate parameters, and then upload the compiled circuits with a table of the parameters, and add runtime on FPGA, stitch this back in, and execute. And this results in significant time savings, multiple factors, both on the host computer at the compilation step and on the FPGA-based control system at the execution runtime. And so this, again, put this in archive. Similarly, we have filed a patent. We're working with the IP office. We're trying to keep these open source and make these available to other academic groups and national labs so that we can collaborate. But we filed a patent so that if corporations would like to use these to benefit from them, it makes sense to license them. And so what I have shown you so far is we have this problem of the abstraction model that is suboptimal, and people are not really working on the abstraction model itself. They're really, everyone, including the corporations, are really working on optimizing the individual boxes. And hopefully what I've convinced you so far is that if you do think about the approach the right way and break these abstraction barriers, you can co-design across these to arrive at order of magnitude improvements. In some cases, multiple orders of magnitude improvement. And so that's, we've already done that work across the middle of the stack with the control system, compilation, and QCVV. And by the way, that choice was strategic and intentional because folks were developing applications and algorithms. They would usually not like to worry about how a quantum processor works. They want to think about their applications and algorithms in abstraction. And the folks who are developing the physical layer quantum processor would prefer not to think about compilation and algorithms and applications. They're just disconnected. But folks sitting in the middle of the stack, they have to worry about both. And that makes this a strategic starting place to do this co-design. And that's why I started asking my teams to do work here. But then the same methodology can be extended to the rest of the stack. And so this is what I would call full stack co-design. And if you do this, I mean, the claim that I have is for a given technology node, if you do the system architecture the right way, then you will have a more performant system. And that means that you might be able to get to quantum advantage a bit faster. So conclusions, where do we stand? A quantum computer is a complex superinstrument consisting of many individual instruments working in concert to allow us to manipulate the quantum state of individual qubits to program a larger collective quantum behavior. The different parts of the stack, including the different instruments, are often compartmentalized and treated as individual isolated boxes and then optimized individually that way. But to arrive at optimal performance, we need to investigate optimal quantum architecture for harmonious design and operation of this superinstrument. And the path to this optimal quantum architecture is through deep co-design. And in this process of deep co-design, we will break the current abstraction boundaries and reformulate the abstraction model for quantum computers. And hopefully, in 10, 20 years, the abstraction model we will have will look different than what we have today. OK, so that is the end of my talk. But then I would like to, since you stayed with me for so far, I would like to also use this opportunity while I have your attention to do a shameless plug. Something completely different. So those of you who know me, who have been interacting with me for a few years, you know that I've been moonlighting as a karate instructor at UC Berkeley for the last 6 years. And I've been regularly traveling to Japan to practice with the highest level masters of karate there to improve myself. And now I'm thinking about opening up my own karate dojo. And what I found is that technical folks are actually really well suited to martial arts. Some of my best students have been scientists and engineers. And so I think this is the perfect crowd to advertise this. And so beginners and experienced folks equally welcome, and contact me if there's interest. And I just have, usually I'm in the news for my science, but last year I got invited to this karate event in Tokyo where almost everyone was Japanese, but then 3 of us were from the US, the UK, and Germany, and we ended up in the official news website of the Japan Karate Federation. So I think that's also cool to put there. All right, I'll stop there.
Thank you so much, Kasra. So questions from the room first, and then folks on Zoom. Azriel, please.
It's going to be a vague question. Sorry for that. Great talk.
Thank you.
So it seems like you're tackling the full problem, all the way from the qubit, all the way to the abstraction and et cetera.
Yes.
If tomorrow somebody tells you, Google or somebody else that put 10 times more money, people or effort,
yeah,
and they build something that is order of magnitude, 2 orders of magnitude bigger than whatever you have here.
Yeah.
Wouldn't you just drop that and just work on what is the problem that you want to solve with a computer?
I would be happy if I saw Google and IBM do this kind of work. I mean, the reason there's room here for me is because they're not doing it, right? So the couple of examples that I showed you, these are pieces of work that should have been done by exactly those types of corporations with a lot of money, with a lot of power, but organizationally, they're not set up for it. And I've had, I mean, this is going to be recorded and put online, so I'm not going to, but in private, I can tell you anecdotes about my discussions with internal IBM scientists who came up to me and congratulated me and said, this is exactly the right way of doing it. And then I asked them why IBM is not doing it. And then, so I'm happy to discuss the anecdotes there. But my hope is that this exact approach would be taken up by folks who have the access. I'm pointing and identifying opportunities here that others are not doing, right? I still believe that the best place for it is a national lab with proper government funding, right? I still believe that because of the type of talent that we have, because of our unique multidisciplinary approach to science that is typically not done in industry. Industry takes multidisciplinary people and then beats that multidisciplinarity out of them and puts them in a box and asks them to do that work in the box. Doesn't have to be that way. There have been really good examples of co-design by Apple, for example. That's why the iPhone became successful, is exactly because they were the first people to do this kind of deep co-design that was not being done by BlackBerry and Android and others, right? So it is possible to do this in industry, but I think that national labs are better set up for it. And I think that in the early stages of quantum computing, as we're in right now, where the profit motive is not going to get you as far, I think for the next maybe 10, 15 years, still the national labs will be the better place to do this.
Any questions on Zoom? Raise your hand.
Steven.
Just waiting for Zoom. No. Okay. It feels like we're still a long ways away from like practical quantum computing. But
Yep.
Is there anything like Moore's law for quantum computing where we're just early on the exponential growth? Or are we still sort of in the slogging our way through linear growth on improvements before it'll take off?
Yeah, there is. I saw this really cool plot by, I think it was Dave Schuster, who referred to something called Sholkoff's law. So Sholkoff is a physicist, is a professor at Yale, I believe, and he plotted the improvements in coherence. And statistically, it does actually tend to follow some sort of a process. I forgot the numbers, but it basically talks about how much improvement we get in coherence times and qubit numbers as, well, I mean, qubit number doesn't really matter on its own. Like when you hear people talking about 1,000 qubits, 1,000,000 qubits or whatever, it's meaningless. Anybody can fabricate 1,000,000 qubits. So the question is, will it do anything beyond what your 100 qubit system will do? And the answer is right now, no. Why? Because the coherence times are low, because the architecture is not right. There's a lot of different problems associated with that. So yeah, there are laws there, and coherence times will improve. There are things that will just take care of themselves because people are working on them. But in the process, we still need to do this type of architecture work.
Other questions? Can I charge in and
Please.
tailgate that one? So what are typical coherence times, and do you have a team looking at that, and what's limiting you in that regard?
Yeah, so the typical coherence time depends on your qubit implementation as well as your qubit connectivity. So for example, in the plot that I showed, kind of this range going from highly coherent and the least tunability and modifiability to the really configurable versions. If you add a lot of knobs to control your qubits in a more detailed way and the couplings and everything in a more detailed way, that gives you more ability in terms of running faster gates and doing things better. But then those same lines act as pathways for noise to get in, right? So then you get lower gate times. So really the right way to think about it is, roughly speaking, the ratio of your gate time to your coherence times and the connectivity of the qubit. So if you have one qubit connected to 4 versus one qubit connected to 2, the 4 is going to have lower coherence times, but longer lifetimes. Lower coherence times, I'm sorry, but it'll have a lot more additional power in terms of needing to run fewer gates to execute the same experiment, which means you get more juice out of it, right? So going through all that just to say that you shouldn't be looking at just the coherence times. Now, that said, the state-of-the-art coherence times right now for a disconnected qubit that is not connected, that is not coupled to anything else in the environment, is roughly order millisecond. And if you have a coupled qubit, then it's order 100 microsecond. And it can be anywhere between, the same qubit, if you put it in a connectivity of 4 system, it can be 20 microseconds, but then you'll have the ability to run 20 nanosecond gates on it instead of having a 300 nanosecond gate, right? So I hope that shows you a little bit.
Great. Thank you.
Yeah.
We're over time. Thanks everyone for sticking with us. Thanks again, Kasra.
Thank you.